the High Energy Seminar. Today our first speaker is Dr. Elaine Winston. And Elaine got her PhD at University College Dublin. And during that time, she was also a pre-job at CFA, where she was working on infrared and X-ray observations of young clusters. And later, she did the postdoc research at the University of Exeter in the UK, and also European Space Research at the Knowledge Center in Netherlands. Currently, she's a postdoc at CFA working with Scott Walk and Nancy Evans. And today, Elaine is going to talk to us about a young cluster at high energy.
Thank you, everyone. Thank you for coming. So yes, today I'm going to speak about Serpent South, high life of a young cluster. This is an unusual cluster that is very young, recently discovered. I'd like to share some results that we have from Chandra. So I'm working here with Scott mainly, and also Rob Goodemuth in UMass Lowell, Tyler Burke he's at Manchester in the UK, but was formerly at CFA, and Tom McGath, also formerly at CFA, but now in Ohio, Toledo. So first, I'll give a brief introduction of star formation. I'm sure everybody knows that already. A little bit of an overview of what we know already about Serpent South, and then I'll discuss the results that we have with Chandra. I'll discuss the identification of the YSOs in the cluster, some of the X-ray properties that we've defined, and also then the broader context of this cluster, so in relation to the rest of the Serpents group and the Aquila Rift. And then I'll wrap it up. So one of my people I used to work with in Exeter, Matthew Bate, works on theoretical models of star formation. So here he has a large-scale cluster, and we can see the individual objects forming along some cluster filaments as the cluster, the gas condenses. So you can see a very dense cluster to the center and little pockets of star formation off towards the edges. So this is kind of what we expect to see when we're looking at some clustered regions, and we'll come back to this later. On a slightly smaller scale as we move in, and this is about 5 to 10,000 AU range, we can see individual objects or small clusters of objects, groups of objects, maybe one or two, forming along these very dense filament regions in little pockets. So again, these would be some individual objects on a smaller scale. So we're probably looking at something in between these in Serpent South itself. So briefly, when we look at circumstellar disks, what are we looking at? With Chandra, we're actually looking at just accretion properties in the young star itself. So we're looking at the actual center here and over to the left. We're just seeing the inner properties as it's secreting material, as it's condensing itself. Young stars are very highly active. So they tend to be 3 to 10 to the 4 times that of the main sequence counterparts. So we can still see them in Chandra at this young age. And they'll continue to be very active up till probably between 10 to 100 million years. And they'll just gradually lose activity and approach the main sequence counterpart level. In the infrared, to which we're going to match these objects, we're going to look at their properties. You see that in the near infrared, we're looking at towards the inner gas disk, and then to the rim of the dusty material in the circumstellar disk itself. And this is the near IOR continuum, moving out into the mid IOR, into the far IOR. So we will be using 2 mass data, which will be the kind of the inner disk. Look at some of the gas accretion lines, but mainly just the inner disk rim here. Into IRAC, which is Spitzer IRAC, which is the planet-forming regions, and then further out into the dusty reservoirs and the outer disk with some of the WISE data. So the Serpent South cluster itself was discovered in Goodemuth et al. 2008 in Spitzer IRAC images from the Gould survey and the C2D survey. Here we're showing it with IRAC. This is the 3.6, 4.5, and 8 micron images in blue, green, and red, in that order. So Serpent South, you can see here it's nicely condensed. You can see a lot of outflows in the green. It's considered a very high protostellar fraction. Oh, thank you. I was wondering where this was. Let's see if we can turn on. So the central cluster region here, you can see some outflows in green. And you can see it has very high protostellar fraction. So of the Goodham et al. Identified 92 mid-IR members of the cluster from the Spitzer data, and half were class 01 and half class 2 objects. They didn't break them down any further than that, but this gives the cluster one of the highest fractions of protostars in of all the kind of the Gould Belt clusters in the nearby regions of star formation. So it's also considered to be that region one of the youngest. And it's considered to be very nearby, although how nearby is something I'll discuss a little bit later. At the moment, they think it's between 200 and 400 parsecs. And when I say it's near to W40, it's about 0.5 degrees away from W40, which is considered to be, it's a high mass star forming region. It's about 600 parsecs away. So here I'm showing it now. I've added in the ACES I observation. These are all the little blue stars that we can see peeking out here. Our Chandra observation was at 97 kiloseconds, taken in 2010, centered on the heart of the cluster, as you can see right in here. We detected 446 point sources in the region, of which about 150 had significance greater than 3. So these are considered to be good detections, solid detections. Using that, then, we went on and combined this data with the existing catalogues in the infrared. So we have Spitzer IRAC and MIPS, which are basically 3.6 to 24 micron data. 2MASS, the near IR, JH and K, and then WISE, which also has 4 bands, which goes from 3.4 to 22 micron. We took those catalogues and matched them to the positions of the X-ray sources with a 1 to 2 arcsecond matching radius, depending on the off-axis distance. So increasing. So in the heart of the cluster, they're all matched to 1 arcsecond. In the outer rim, 1.5, and then 2 around the edges. Using those catalogues, then, we find that we have 75 matches between the X-ray and IR catalogues. And what I'm showing here is the green are the objects identified with Goodham et al., and then the white objects are what we're picking up with matches to the X-ray catalogue. So you can see that while the known IR sources are quite condensed along this filamentary region, we're getting a little bit more of the cluster out around the edges. So it's extended slightly beyond what it was considered to be originally. How do we use this? This is just the typical, this is the IRAC diagrams. These are the color magnitude and color diagrams. Upper left, we have the traditional IRAC. Here is IRAC with MIPS. This is 4.5 minus 8, and we use this to get rid of some of the contamination. And then here is the WISE data. So traditional IRAC, you can see that we have a lot of objects with excess emission. A few down here which are more likely to be transition disk. And right in the center here we have objects that have no excess emissions. They're most likely to be the class 3 traditional diskless objects. For a cluster this young, we're interested in finding out how many of these diskless objects are actually present. Again, you can kind of see some of those here that just have a small color but nothing in the 8-24. It's a very embedded cluster. This is actually quite a large number of detections in 24 with very strong colors. So we know it's quite embedded from this and quite young. And down here, this this diagram is basically used to identify cluster members and pick out objects which are most likely background AGN. So you can see that possibly these detections down here, these 2 and perhaps these 5, in fact, may be background AGN contamination, which we will then remove. So what we learned from all of this, this is a rather colourful image, but over here you can see in the key that what we've known is we had previously known 92 objects, which were split into classes, class 1 and class 2, 46 in each. What we have is we have 75 matches. From these, we identify 63 YSOs as being bona fide members of the cluster. So we find 9 class 1s, 11 flat spectrum, so we're splitting now the class 1 between the class 1 and flat spectrum objects as well, which is slightly more evolved. Class 2 we split into 21 now, and then we also have transition disks and class 3 objects. So previously, Goodham et al. Didn't use the MIPS 24 micron or 70 micron to split the class 2 objects into objects which are considered transition disks. So they're a little bit more evolved and perhaps only have emission at the longer wavelengths. However, we're now using the MIPS24 and the WISE longer wavelength data, so we can see objects that don't appear to have a little or have no excess emission in the inner disk, but are showing an outer disk emission. And for this, we found also using that data that there are 10 class 3 objects that even out as far as the WISE and MIPS band don't show any excess emission at all whatsoever. And then just the remaining 12 objects were only detected in 1 or 2 infrared bands. And so they could be background objects, but also, as if you look here, as this is color-coded, there are some that are actually in the center of the cluster or are associated with other known members. So perhaps we're just missing, given that it's a very embedded cluster, we might just be missing photometry for these objects, so they could be real, and we will discuss them more in detail in our paper. So in kind of total some of the numbers that we detected, over here I'm just putting the column what we find for Serpens North, which Serpens South is considered to be part of this Serpens region, and Serpens North is or Serpens Main as it's often known, is the most well-studied object or cluster in this region. So with Chandra, we're detecting 33% of the known objects previously identified, which is a little bit lower. We usually detect about half in Serpens North. We're down to about a third here. Again, if you're just looking at the identified class 1s and class 2s, they're both dropping to about a third as well, where again previously they were closer to 50%. This is most likely due to the fact that it's a more embedded cluster, so we're picking up less photons, and also these things are younger, so perhaps they have a lot more material around them, so there's more absorption of the X-rays. Protostellar fraction detected in X-rays, these objects. This is the class 1 in flat spectrum. Over the class 2 transition disk in class 3 is about 46, and in Serpens North it's 39. So again, there's a higher protostellar fraction detected in the X-ray, so it's a much younger cluster according to the X-ray detections. And again, disk bearing fraction, this is basically the ratio of the premium sequence class 2s to the class 3s. So again, looking at this, if we just take class 2 to class 3, we get about 32%. If we split the transition disks here, one of the problems with the transition disks and comparing to the other clusters is that we don't always have the longer wavelength data. So just taking a slight split between objects that would have been classified as class 3 in previous works with objects which would definitely be known to transition disks, putting in here, so you get 37. So still, this is a lot smaller than Serpens North. So it's indicating that this cluster is probably less than 1 million years old, whereas Serpens North is considered to be 1 million to 2 million years, or at least have multiple populations around the 1 to 2 million year range. So I think that we've actually confirmed now with the Chandra data that even though we're identifying perhaps more evolved objects, it's still likely that the cluster is extremely young. So the X-ray properties, we're going to make a comparison. The main thing that we're going to discuss is the NH to AK ratio. So this is the hydrogen column density as defined by the X-ray models of the individual objects against the extinction measured at the K band. So this is basically a dust to gas ratio. The standard ratio of the ISM is about NH about 1.6 to 10 to the 21 AV or 10 to the 22 AK from Young et al. 2003. We've previously worked in Serpens North and NGC 1333, another young cluster, at about 240 parsecs in the Gould's belt. And unfortunately, I don't think that's very clear, but if you see that this line up here is the ISM standard, and that both clusters joined together are actually below this, and they are at about 1.8 of the expected value, so they're about half of the value. On the top here we have RCW38, which is a much more distant cluster at about 1 kiloparsec. It's also much more massive. There's a lot of massive stars in it, and it's following the expected ISM value quite well. So what we think we have here in this case is that we're having grain growth in the dust around these young stars, and that's causing this ratio to appear to be lower. And these are the results now that we have for Serpens South. And again, it's even a little bit lower again. It has about 0.73 by 10 to the 22 AK if we fit to this line here. So actually this will be the standard, and then this is the fit that we have to the data. And in this case, the small squares are class 3 objects and the triangles are class 2. So you can see there are a lot of these class 2 that are actually causing the trends. So we think that these objects with disks are actually processing their dust. So this would be planet forming, or at least the beginnings of planetesimal formation being observed in these young clusters. One of the main things that we can now do with the X-ray data is to form the X-ray luminosity function. And this will go back and discuss the distance to serpent south. So as I said previously, the distance to serpent south is unknown. When the cluster was identified by Goodham et al. In 2008, it was considered to be co-moving with serpents north, which also has a history and distance, can go from anything from, we'll see this put down there, so the Zib et al. 2010 have put it at 410 parsecs, which is kind of the standard at the moment. Previously, it was considered to be at 260 parsecs, which was Stars et al. 1996, and that was from essentially extinction to the face of these clusters. So it's considered to be at least a measurement of the front edge of the clouds that we're seeing. The Zib et al. Measurement, I'm not sure I'm saying that right, is taken from EC 83, sorry. And this was one object in the center of the serpents cluster. And from, they've been monitoring this object, and from its movements, they assess its distance to be 410 parsecs, and that's now considered to be the distance to the serpents north region. In a previous paper, we used the XLF here, the X-ray luminosity function, to measure the distance to serpents north from our previous Chandra observation of the region. And we found the distance fit to about 360 parsecs. So given a range on this, it's probably closer. It's between about 340 to about 390. So in some ways, it's a little bit more consistent with the newest measurement of the region. And then this lower plot here, evaluated 7, this is the distance of 600 parsecs to the W40 region. So again, this is a massive cluster, about 0.5 degrees away and from serpent south. But it is unknown whether or not they're associated. So by looking at these plots, we see that of all the distances, basically the fit to 260 parsecs seems to best fit the data that we have for serpent south. So this is now essentially, instead of putting it associated with serpents north, we're actually claiming it's slightly closer than serpents north and completely unassociated with the W40. So we are unsure. This is a very complex cluster region. So there's the whole Aquila Rift. It seems to be at numerous distances. So to discuss that a little bit further, I'm just going to show you pictures of serpents north here. So here's serpents north, the main cluster, and this is SIR G3, G6, which we're planning to observe at the moment with Chandra to get an estimate of its distance. And you can see that these are associated here. This is, again, this is just a mid-infrared image. And these are the IRAC images of the clusters blown up. So you can see that there is some associated region. Now I should point out that this is about 3 degrees north of serpent south. But yet, when you compare the two clusters, they are about the same size, about the same scale on the sky, and they seem to have similar numbers of objects associated with them. Yet, this one, serpent south, has far smaller, has a far higher protostellar fraction and smaller number of class 3 objects. But so perhaps younger, but otherwise similar. So how can we discuss these? Is there any kind of basis for the XLF having a difference? Well, we've also had Piliteri and Woke et al. Have published a paper on the X-ray luminosity function and the distance to Kappa Ori. And if you can see here, this is the end of the Orion A, L1641 south, coming down here. And this is Kappa Ori in the center. And here we have Planck, WISE, and CO going across here in these 3 images. And you can see that there's a bubble forming around here. And they've used observations. So if you see the slide outline, you can see the XMM observations and Chandra observations of these in the X-ray. And you can see that they've taken 2 regions and found that, in fact, although they appear to be contiguous on the sky and associated, using the XLF, they found that, in fact, the capillary clusters are likely to be at a distance of 250 to 280 parsecs, whereas Orion A and L1641 are at the distance of Orion of about 400 to 450 parsecs. So there is previous we're finding this in a lot of places, that there's quite a complex three-dimensional structure that by just looking at as we have previously and observing them in the infrared, we don't find this structure. We're kind of pushing everything onto the 2D and associating these regions. Whereas in fact, we're finding, at least here and in serpents in the Aquila region, that there's a huge three-dimensional structure, and then this will have knock-on effects for how we actually judge the age of these clusters and cluster the mass of the objects in these clusters, and also just the IMF in these regions and such. So I think we're moving towards this, using the Chandra data as a first step to understanding the three-dimensional structure, which hopefully when we have things like Gaia, as always, down the road and proper distance measurements, we'll actually be able to look into in more detail. So here I'm just comparing Serpent South in blue, right in the center. This is Serpent's North. And this is NGC 1333, which Feigelson et al. Have used along with the COOP data as kind of performing this, finding the universal, as it were, IMF, which is based on the log LX of 29.3 with sigma of 1. So you can see that the fit to these data then, SER South is fit best at 260, SER North at 360, and then this is the standard distance of 240 for NGC 1333. So the two Serpent South clusters don't appear to be at the same distance, at least, or associated directly, as previously thought. So to give a kind of a wider kind of pictorial view of where we are, this is Serpent South right in here, and this is W40, and this is the kind of central OB cluster in here. So that's about 0.5 of a degree away. So if we then, this is the Spitzer-Iraq imaging of the region. So if we zoom out then and take a look at the Herschel image, you can see again that we have, this is Serpent South in here and W40, and you can see that there's long filamentary structures here with little clusters being picked up in these little regions along the filament. And it's very hard to tell, as this kind of goes up off to the side, whether or not W40 and Serpent South are associated. On the sky they appear to be, but as it's still the distance measurement to W40 is still 600 parsec, and we're putting this as about a half to a third of that distance. So, although they appear to be associated, where is then associated with Serpent's North? So if we then look at just some extinction mapping to this region, we can see that this outline here is basically this image right in here, slightly rotated, and again this W40, and there's Serpent South. And right up here we have Serpent's Main or Serpent's North, and this is G3, G6. So you can see them coming down here, and whether or not this cloud is associated, this filamentary structure, or how the entire region is associated with one another is something that is obviously still very unclear and something that we're hoping to work towards. So we are continuing to work. As I said, we have Chandra observations proposed for this region here to see whether there's an association in distance along this region. And also we continue to work once these Gaia provides some distances, hopefully. Unfortunately, that suffers from extinction, and these regions have very high extinction. So we'll see whether what we get out of that in the long run. So thank you very much. I was very clear just listening. So just to round up, we have a Chandra observation, 97 kiloseconds, that we've used to observe Serpent South. We've detected 63 YSOs, 34 of which are newly identified members of the cluster. We still have a very high protostellar fraction. The dust to gas ratio is below the standard ratio, so this is standard is about half of the standard ratio. We've determined a new distance of the cluster to 260 parsecs, which means it's not at the same distance and possibly not associated with Serpent's North, for which it was named. And again, still not associated with W40 either. So we have a very complex structure in the Aquila Rift. And hopefully in future, we will be able to, with the onset of Gaia and other data, we'll be able to work on this a little bit more and create a three-dimensional structure for these regions, from which we better understand the cluster and the young stars as they form. Thank you.
So when you're talking about the only talking about grain growth that occurs within the protoplanetary disk, or does that whole area then experience a different extinction?
Well, it's difficult to tell because you're also looking along the line of sight. So in both cases, you're getting measurements along the line of sight to the object, so within the cluster itself material, and then also the dust in the disk. So while we consider it's possibly, we consider it's most likely within the planetary disk itself, but it could also be grain growth in the region, and that's possibly why RCW38 doesn't show the same because it's a very high mass cluster, and the OB stars are possibly blowing out all the light grains and such and preventing grain growth in those regions.
About the identifying the distance based on the XLR, is there any sort of dependence on the completeness on the low end of the population?
Yes, and that there will be a problem. We're actually, there will be to some extent. If I go back, however, we're basically fitting to this region here. So for all of the clusters, in fact, so definitely we have most of the NGC73, which is why we're looking at using it as a standard. But there is a certain fall off here. But considering that we're matching just in the kind of 29 to 30.5 region, there isn't a huge fall off. And since we think that we have, as you see, we think that we have actually completeness to this level. So while we would expect that we find more like low mass objects, they'll just complete this curve. So there is some error involved in that, and that will probably give you, maybe 20 to 30 parsecs. Sorry.
The incompleteness comes in determining which of those last two bins you end up fitting to the log normal and how you weight them. So that's fitted to the log normal, and so when you minimize your chi-square, all the incompleteness is going to do is weight those last two windows.
Okay, I'm not expert on this, but so then I guess the distance comes out to match the model and relative to each other on this diagram, I guess. How solid is the model to run the distance? Is there any some populational difference? Well, you saw there's a difference in the ratio of some classes from another.
Right, so the basic argument is that within the first 10 million years or so, the X-rays are roughly constant. And then the distance to 1333 is independently determined. That one's got what's the parallax determination for 1333?
Yeah, it's 240.
So that one, that's an agreed upon distance.
Yeah.
And so everything's off from that.
It's also mainly determined from the Cooper-Ryan data as well. So we just use NGC33 because I have access to that data previously. That's why I'm showing it here. But Feigelson et al. And then Walk et al. For Lake H Alpha 101, and then the Coop data. So they've used this. So it is quite an empirical idea, but they have, given that the Coop survey is very deep, they consider that they have completeness there. And so they're modeling it to fit to that, and then Lake H Alpha 101 as well. So you can see in all these clusters where they do have deep observations that it does fit this empirical formula. And the cluster serpents tends to be very embedded, very deep, and very young, even in comparison to 3033. So yeah, we tend to see the lower bins aren't complete there. But you can see that, yeah, we're picking up all the brighter objects, and yeah, it's just the last few bins that we wouldn't be completing.
So related to that, what's your estimate of your mass, the mass at which you are essentially 100% complete?
For the circumstellar data in the X-rays, I think it's probably just about 0.5 solar masses, maybe 0.3. But yeah, for completeness, yeah, we're not anywhere near the brown dwarf limit or anywhere. We're just not seeing those really, I don't think. Incompleteness. We do see some of the objects. I didn't show the, actually I didn't include it unfortunately in this plot that we're still working on, that we do have a K-band completeness limit where the X-rays, we do see objects down to the completeness, so we're seeing down to about K-band of 14, 15. We're not complete obviously in the K-band either at those, and we do see X-ray detections down to that level, but the fall off is quite large. I mean, you're not any more complete more than about 13, 14.55 probably.
Any other
However, today I'll be talking about the fully science part, not so much about the instruments we're using for. And I'm going to talk about how I and my collaborators are using high-mass X-ray binaries to probe clumpy winds of giant stars. And like the two people whom I want to point out is Natalie Hell, who is doing the lab measurements over at Lawrence Livermore, and Maria Hirsch, who is kind of also mine PhD student over in Germany, and a few other collaborators. So why are winds of O and B stars interesting? And that's kind of really cool that my talk is after Elaine's, and that's because, I mean, winds on high-mass stars are really important in star-forming regions because they can trigger or inhibit star formation. They also can impact chemical evolution of stuff that happens around them. If you look at winds of those O and B mass stars, they are line-driven. So that means scattering of the stars' UV radiation drives those winds, and the mechanism that does this kind of work is called after Custer-Abbott-Klein mechanism. The winds have very high mass loss rates of over 10 to the minus 7 solar masses per year, and very, very high terminal velocities. However, the problem with those winds is that the line driving, so this pressure of radiation on UV lines, is intrinsically unstable. So if you have the smallest perturbation in there, and this is what happens in reality, those perturbations are going to grow rapidly. You are going to get shocks that then will lead to formation of dense gas shells on what we call stellar clumping. And what you see here is just a simulation showing 3 different runs of clumping with different parameters. And color gives you the difference to the average density, and you just see how structured those winds are. There are multiple observation lines of evidence that shows that O and B star winds are clumpy, many of them coming from the optical. So the clumpiness itself is nothing new. But the problem is, if we look at individual stars, whether in optical or in X-rays, we are always going to measure the whole ensemble of clumps. So we are not able to look at actually one individual clump and see what is the structure of this clump. We are just looking at the whole thing, the whole stars. And this is where high-mass X-ray binaries come in. So just as a reminder, a general X-ray binary is a compact object, usually a neutron star or black hole, that accretes matter from the companion. You have all kind of accretion and ejection processes close to the compact object, and bulk of the radiation is emitted in the X-ray range. And the thing with high-mass X-ray binaries is, on one hand, the wind from the companion influences the X-ray production close to the compact object. So kind of flares are defined by how much matter is falling onto that. You can have like long-term variability may be defined by the winds. You have something like super fast X-ray transients that have been discovered with integral. But at the same time, if you don't look at the object, at the compact object, but at the star, or its winds, then the radiation from close to the black hole is an effectively X-rays the wind. So you have kind of a small X-ray source sitting in there, and the X-rays go through the wind like they would go through our body and getting absorbed in the individual clumps. So we have in situ probes for those winds, and we can look at different parts of the winds at different orbital phases. However, it's of course not that simple, because otherwise everybody else would have done the science before. There are 3 main challenges. One of them is accretion structure. And kind of as this artist's impression already implies, the fact that there's neutron star or black hole sitting in that wind is actually going to deform the wind. So you have things like accretion at photoionization wake. You have something like a focused wind, so wind that is kind of concentrated towards the compact object. Also, if you look at the analytical and numerical simulation in literature of the interaction of compact object with winds, you're going to find out that people have done a lot of work on homogeneous winds, but people haven't actually done, I guess, almost any work on clumpy winds. I do understand why. It's really, really complicated. However, so my solution to that is to see that not as a challenge, but to see that as a chance to actually learn about this accretion structure. the second problem is that X-ray binaries, even the low mass ones where you don't have the complication of the stellar wind sitting in there, are intrinsically highly variable. This is Cygnus X1 that I'm going to talk about in a minute, and it's 16 years of Cygnus X1 observation with RxT-ISM, and that thing is highly variable. So you really need to take into account this kind of variability that is intrinsic to the compact object to learn more about the winds, because you can imagine when the compact object is really, really bright, the wind is going to look different, to interact differently with the compact object than when the compact object is less bright. Well, the solution is we'll go and talk to X-ray binary experts, and this is how I ended up doing this kind of work, because I did my PhD actually looking at variability of X-ray binaries in all time scales. To learn more about the accretion. I did learn stuff about accretion, but I also realized, oh, we can also use what I learned to learn more about the winds. And the third challenge is reference line energies. The clumps that you're looking at in the winds are somewhat colder than all the stuff outside. So what you are seeing if you're looking with Chandra T2G are lines, absorption or emission lines. But you're not seeing absorption lines like K alpha or helium triplet. You're looking at lines at low ionization energies. And then what you are seeing is that your observed energies is not the same as your reference energy. Wonderful, I got a Doppler shift. And then you look at your lines, all your lines have different Doppler shifts, and you realized, oh, maybe my reference data aren't really well. And this would have been especially important. Well, it's important for everything. It's important for Chandra. It's going to be really important for microcalorimeters. And the solution to that is, well, go into the lab, and this is something that Natalie Hell is doing, and actually measure this line energy as an EBIT. And this is just kind of a very rough schematic of what an EBIT looks like. So you have atoms confined in electric field, electromagnetic fields, and then you it takes a lot of time, the ions that you want, and measure the line energies. And there's a paper coming out on silicon and sulfur measurements of silicon and sulfur measurements of L-shell transition lines that should be on arXiv, and the next day it's almost accepted. So, and I'm going to walk you through like 3 very short overview examples of the kind of work that I'm involved with, where we try to use high-mass X-ray binaries now really. So first source that I will be talking about is Cygnus X1, is the one source where you've seen the long-term light curve before. And this is a 2-scale sketch of the source. So you have O-type primary. You have the black hole sitting here, and you have an orbital inclination of about 27 degrees. So this is orbital phase 0. You're looking really close to the companion. And this is orbital phase 0.5, so you're looking much further away from the companion. So those are your sight lines. An orbital period is 5.6 days. This is going to be important. That means that we can cover this 5.6 days really well. And the first data that I've been using was also the data that I used to do my variability, and that I used to look at evolution of spectral state of the source. And it's 16 years, 1996 to 2011, mainly biweekly observations with RxTE. That's about 2,700 observations. And I'm just using the hard state data. So I'm just using the data when the central black hole is not emitting much in the soft X-rays, because this is where I expect that the influence of the black hole on the wind is going to be the smallest. And this is also the data where I can actually use RxT data well to constrain absorption, more or less well to constrain absorption. So what you see here is orbital phase plotted twice. On the y-axis, you have measurements of equivalent hydrogen column density, so a measurement for absorption towards the source. In red, you see the average values. In white, you see the median, just to guide your eye. And well, you see how kind of they're all over the place with a certain structure in there. And out of this data, I'm picking one long, stable hard state because I want my source to behave really well. And between 2006 and 2010, the source spent 4 years pretty much just staying in the hard state. And I'm going to look at this data and trying to explain this variability of absorption along the orbit. And kind of the one toy model that exists in the literature is just the classical Kelvin-Abbott-Klein model. So what you see here is the star sitting here, the black hole. You have spherically symmetric wind, except in a cone around the black hole, which is kind of a toy model for focused wind. Color represents the density of the wind. You have the same data as before here, so my kind of long hard state. And the green is the best fit model, and as you can imagine, well, it doesn't fit the data well. We would have expected that because we see far too much structure in here, those individual measurements that are far too deep. So we really need something that has clumping in there. So we went and talked to people who actually developed clumpy wind models, mainly from the optical and theoretical side. Those are people who partly haven't touched X-rays in their life. It's an interesting conversation, just kind of trying to establish the same terminology. And so the example I show is from work from John Sundquist, who was involved in the work. The models were models by Rich Townsend over at Madison. And Rich and John told me, well, their models are equivalent. They behave the same way. They tested that. I trust them. So what you see on the plot are, so it's always a star in the middle and kind of different wind with different amounts of clumpiness in there. So what we assume is discrete spherical clumps, which is a zero order assumption. We assume what we call a beta velocity law. That's a law for how the wind and how the clumps move to the outside. And we don't include a focused wind component in our data yet, just because we want you to try, well, do the models work at all in the first thing? What we also know, we know the stellar parameters of the companion of Cygnus X1, we know the terminal velocity, and we know the term mass loss rate. And then we have two variable parameters in our model. One of them is a number of clumps n, number of clumps per given time interval, and something that is called the terminal porosity length, and that depends on the radius of the star, the initial radial size of the clumps, and the number of the clumps. And if you spend some time thinking about that and talking to people who developed these models, then you realize that this terminal porosity length gives you the average free path length of photons between clumps. There's a bit of thinking involved behind that. Just trust me. That's what it is. And now I want to compare the observations with the simulations. And for that, it's not quite that useful to look at the whole distribution because, well, how am I going to compare that? So what I do here is each square up here shows you one orbital phase range. So here the orbital phase is 0.0 to 0.1, 0.1 to 0.2, all the way to orbital phase 0.9 to 1. And what you see in blue is the histogram of NH values. So around 0.5, so that's was the lowest point of my distribution. My distribution of NH is kind of all at the lower limit, so all small values in NH, and it's very spiky, so it's very well defined. Like it's always about that NH. While where you have seen a lot of peaks of absorption, you have this broad distribution that is also shifted to higher values. And what we did as a next, we computed a grid of different clumpy wind models, and then assumed, well, there sits an X-ray. So this is our grid of models. Here sits the X-ray source. This is our line of sight. Let's sum up what the absorption toward that source is. And then we plot that here, and I plot that for different values of this porosity length parameter. And if you see, well, if I assume a porosity length of about 0.1 stellar radius, data doesn't look like model, or model doesn't look like data. If I assume 10, it kind of looks better, but it's still not very convincing. And somewhere in the middle, it looks like the data. It's not perfect. We are not saying that because we know that our model has a lot of assumptions right now that are perhaps not the most perfect ones. But it shows that such clumpy wind models, assuming that what we know about the source can explain this kind of behavior, and we didn't have a model to explain this behavior before. It also gives us an estimate on the porosity length that agrees with what people get for single stars. That's a really good thing. So can we look into individual clumps, because that was kind of also more the whole ensemble of clumps and not individual clumps? Yes, we can, but for that we have to use Chandra. And what you see here are 3 observations taken with Chandra, all around orbital phase 0, so all when we are looking really close to the star through the densest part of the wind. What you see in the upper panel is just the count rate, and you see the count rate dipping, and at the same time you see in the panel below the hardness changes really, really drastically. If we now define different dipping stages, so different they depend on hardness and on count rate together, and extract spectra for individual dipping stages, this is what you see on this lower panel here. And just take into account, so the spectra are not really so much brighter than the other, we just multiply them. They're about the same brightness above, say, 4 kV, and below that, where the absorption comes in, the shape changes really drastically. And then we are going to zoom in on the silicon region. We've done the same analysis for the sulfur region, but I'm just going to show you one plot from one of the 3 observations. And this is here, and from the lowest part to from the upper panel to the lowest panel, your dip strength increases, so you get more and more and more absorption. And what you see here, so you have the different ionization stages of silicon marked here. So that's the fully ionized silicon, and over here is silicon 7. And as you see in the non-dip spectrum, you see almost no silicon 8 and no silicon 7. And as you go into the deeper spectrum, into the deeper dip, as your absorption increases, you start seeing lines from these cold ions. So what you are looking at, what we think, like all those lines also have the same Doppler shift if we use the newest reference values from Natalie Hall. So that means they also really, this is matter that also at least moves together, in some way belongs together. What we see, what we think is onion-like clump structure. So something like this here, where in a non-dip, we are looking through the hot phase of the event, where we just don't see much absorption. And in the strongest deep dip, we are looking through the center of the clump that is the coldest. Do we see something like that in other sources? Because Cygnus X1 is kind of the one brightest object out there on the sky. So I went out and took the other bright X-ray binary, really bright X-ray binary out there, Vela X1. And this Cygnus X1 was an O-type supergiant. This is a B-type supergiant. Here we have an eclipsing binary orbit, so the star and the neutron star are in the same plane. And this is also a 2-scale sketch of the source. So my neutron star is really, really close to the companion. When it comes to Vela X1, we know that the absorption structure is pretty complicated. We don't have an accretion disk, but we do have an accretion wake, and this is kind of the focusing of the winds to gravity. And we have photoionization wake. This is where the shocks between the wind that comes from the star and the ionized region around the neutron star happen. And if you look at the absorption along the orbit, this is what happens with absorption along the orbit if you average over many, many, many orbits. So you have an eclipse here. When you look at orbital phases between 0.2 and 0.4, so if you look from this direction here, you have no accretion wake and no photoionization wake in the way, so you don't have much absorption, and then your absorption increases. And what people so far have usually been interested in is the times when they actually look through the photoionization and through the through the accretion wake. Why? Because if you look at the spectra at different orbital phases, and this is like a really amazing work by Watanabe et al. From 2006, then you see that at phases 0.5 and at the eclipse, you see a lot of lines, so you see a lot of structure with that you can actually use to learn more about the gas, about the accretion and photoionization wakes. However, they said, well, at pi 0.25, we actually don't see anything, which I found kind of surprising. So what I did, I went back and used the archival data and looked at the data, and it's the same plot in a way that you've seen for Cygnus X1. On the upper panel, you have the count rate. In the lower panel, you now have a hardness. Well, for Cygnus X1, it was actually the softness. So you have higher absorption here when you have this higher hardness values. So I'm, in a way, doing the same that I did for Cygnus X1. I'm taking two different spectra, so one in white and one in gray here, and looking at them individually. And, well, the spectra themselves look really different. And at the same time, if you look at the line content, once again in the silicon region, because that's the one where we have the best reference values, the line content in the two observations actually looks really different. And I'm just going to take a look at the high absorption spectrum. So we used newest lab reference values, and I did like the usual iterative fitting process where I, to increase the signal to noise, also try to tie lines with similar blue shifts. And what we get is, so we do see the K-alpha line, and we do see the two of the triplet lines. And those high ionization lines have one velocity of about minus 300 kilometers per second. At the same time, we do see those low ionization lines, and those have a different velocity. So what we likely see is that we have the ionized part of the wind and the less ionized part of the wind, so the colder part of the wind, moving with different velocities. So I think what we do see there are clumps. What I don't know are those wind clumps, or is the accretion wake perhaps clumpy? Because if you look at simulations run in, well, 1990 mainly by Blunden et al., you actually see that the accretion wake could have clumps. In any case, this is really, really interesting, I think. And this is something we are going to look into more detail. So if I want you to remember three things out of this talk, and it's one, high mass X-ray binaries are actually excellent probes for stellar winds. Or two, winds are clumpy. And third, check for variability, especially if you work with high mass X-ray binaries. Something interesting may be in there in your old data. So in SIGX1, we can show that clumpy winds can actually describe the absorption variability, and we can use them to absorb wind porosity. Also in Cygnus X1, we can actually see this onion-like clump structure with colder, less ionized core of the clump. When it looks to Rayleigh X1, well, we see signs for either wind clumps or patchy accretion wake. In any case, different velocity for hot and cold medium. What is the future? Well, there's an amazing Chandra observation of Rayleigh X1 forthcoming that I'm really, really excited for. And for the future, of course, microcalorimeters, something like Athena, where I'm part of the endpoints of stellar evolution group that looks at high mass X-ray binaries as probes of winds, among other things. Because with Athena, we will be able to either look at much fainter sources, so to increase our sample size, or in cases of Rayleigh X1 and Cygnus X1, we'll be able to look at much shorter time scales and actually grab individual clumps moving into the line of sight and look like just at what happens with one individual clump. So exciting stuff forthcoming, and thank you.
So it looked like in your Cygnus X1 phased observations where you sort of laid out the onion skin, I don't know if it's phase 0.5 the way you did it, but the one that was central to the onion looked like it actually had an emission feature in the silicon region.
That's the forbidden line.
Yes, so,
yeah.
That's a true emission feature.
Yeah, yeah. So if you go to if you go to extreme depths, so kind of even more than what we look in here, you actually start seeing emission lines. But it's really, really pushing the data.
Yes, so this is actually referring to your Athena. Are you telling me that the clumps are extremely sparse? So when you look at any given line of sight, there will only be one clump between you and it?
This is something we'll have to think about. Given what we see in Signal 6, what we see in Chandra, so where we actually see kind of the continuum of non-clumps and then kind of clearly well-defined dips, I would say that the clumps are sparse enough, or if they're further away, they just kind of disperse, so they're not important anymore. I can't guarantee that every dip is one individual clump. We don't think so, but we can. So if I go back, kind of especially with something as clearly defined as this one thing here, so we do think that this may be actually one big clump going through the line of sight. Something like this structure here is more likely more than one clump going in there.
How much mass is in those clumps and in the rings?
95. So the clumps are 95% of the mass, but 5% of the volume, kind of, which is roughly estimate, or 90 and 10. So something in this order of magnitude. So most of the actual mass is actually in the clumps. They're important.
And the velocity difference? You have that?
Sorry?
You have hot and hot, medium, and the clumps. Is there a velocity difference between these two?
That's something in Signal 6.1, I don't think that we have that right now. We did measure both, but I'm drawing a blank on comparing right now. I would have to look up the numbers and see what we see or not.
How does the clumpiness and winds vary with the luminosity class? I've been looking at some of this for a project we're working on, and the claim has been made that main sequence O-stars have much more clumped winds than supergiants, but you're already at remarkable clumping at 95%.
Yeah.
So.
Honestly, I don't know, because from my own approach to literature, I have the feeling that people have a lot of different opinions on that. As the same as where the clumping starts, so where you have actually clumping as close as, 0.1 stellar radius from the star, or whether you need to get further out. I can tell you what we do see for those particular stars, but that has in a way to be taken with a grain of salt, because those are stars that also have the companion that may influence the stars, that will influence the shape of the star itself. I'm honestly not sure that we are at the stage where we can use this to answer your question. I'm sorry.
So the clumping affects what you would estimate for the mass loss rate
Yes.
for O-stars. What is the implication of your clumping rate for example, a standard Vink type prescription? So that's not something that I myself in any way ever looked in. Thinking back at what people have done in literature, I think the estimate from X-rays versus the estimate from the optical were off by a factor of about 10. And assuming that clumpiness helped to reconcile them. But that's all I can say about that right now. Everything else I would have to kind of sit down and think more about that. But taking into account clumpiness is really important for the mass loss estimate in the bigger sense. But I think people are actually by now doing that. I hope they do.
What about other old supergiant systems? LMCX1 is faint, I know, but 1700 minus 37, or SEN X3, or also show clumps, or have they been investigated?
Some of them have been. They are not bright enough, and I'm not saying I'm not on purpose not saying which one have been investigated because I'm definitely going to remember it wrong. So there's some work that Felix Fürst has been doing with work similar to what I've done with RxTE data, looking at integral data and looking at short-term variability in those sources. So yes, a lot of those sources are also, any wind from an O or B star is going to be clumpy, and then it depends where exactly your compact object sits, where you actually get this clumpiness, or whether you get overwhelmed by effects that happen close to the compact object. Most of them are clumpy. I don't think that for most of them you can do the detailed Chandra studies, just because the sources are mainly too faint, unfortunately. So that's really microcalorimeters, or Arcus. Arcus would be also amazing.
Now let's thank all our speakers today.
Okay, how can I turn it off? Okay. Hey, good. Thank you.